Hello everyone. In this session, we are going to be looking at matrix equations. The topics I will be covering. First of all, we'll be doing a recap of linear systems and vectors and vector equations. Then use matrices to describe a linear system. See a connection between the linear systems of equations, matrix equations, vector equations. And see how spanning sets and columns of matrix they are related to each other. Finally, the properties of the matrix vectors product. Let's start with the recap. The first thing is going to looking at linear combinations of vectors. Suppose we are given V1, V2, Vp vectors and some scalars, say C1, C2, Cp, then the vector which is defined by the linear combinations of these vectors, which simply means that you are multiplying a scalar, one scalar with one vector. And if there are p vectors, you have p scalars, you multiply them, and then you add all these scalar multiples of vectors. And when you get them together, you get one vector, which we basically say is a linear combination of the vectors v1 to vp with weights or scalars or constants or coefficients c1 to cp. So let me write them again. I did that in when we were doing the session, video session on vector equations. So I'll be going, kind of going between the weights or the scalars, or I sometimes may call them constants. Sometimes I might even call them coefficients. Okay, either one of them. Now these weights in this linear combination of vectors, they can be any real number. They can be all zeros also. Okay, let's talk about a spanning of a set of vectors. So we just started with the linear combination. So first is, suppose I have a set of vectors, v1 to vp, and I look at all possible linear combinations. Okay. The next is when we gather all these possible linear combinations and put that together in a set. That's called a spanning set of vectors in a very simplistic form of it. So let's look at it in a proper definition mode. If v1 to vp are some vectors in Rn, any dimensional space, then the set of all linear combinations, important, the set of all possible linear combinations of v1 to vp, okay, is denoted by the span of the set v1 to vp. Now this spanning of this set of vectors, it is also called the subset of Rn, spanned or generated by the vectors v1 to vp. We can also refer it as the collection of all vectors which can be written in the form of the linear combination of the vectors v1 to vp with scalars c1 to cp. Okay, now let's look at a matrix product and a vector equation. Now let's look at the matrix product AX. Now this was the very first class I started in this course, matrix products. So what is a I'm just going to, I hope you guys are very comfortable by this time. So I'm just going to write down the matrix product. And one very important thing to remember is, in a matrix product, the columns of the first matrix should equal the rows of the second matrix. So if I'm writing the matrix AX, this matrix product can only be possible if the number of columns, so how many columns this matrix A has? It has 3 rows and 2 columns, and the vector X has 2 rows and 1 column. So this matrix product is possible because the number of columns of A and the number of columns of X are exactly the same. So we have this matrix product now. write these two matrices. Now remember the rule. So this new matrix would be a matrix of the kind 3 by 1. And to get the first row of this new matrix, you will be writing this one as, just to recap, so it will be what? 1, 2. You will be taking the first row of matrix A and multiplying it by the first column of the vector x, which is x1 and x2. Then I hope you guys remember, you multiply 1 with x1, 2 with x2, and then take the addition of that. And that's how we get the very first row of this new matrix, AX. Similarly, we get that for the second row and the third row. Okay, now that's a matrix product. What now we're going to do is, we're going to look at the matrix product and apply the things we learned about vectors in section 1.3 on vector equations. So look at this vector. So clearly it's an addition. I can easily write x1's, these vectors, this is, if you think of this one, this is the vector u plus v. I can separate them. You know, it's basically addition of two vectors, all the vectors x1 and all the vectors x2. You can write this as u plus v. It's basically addition of two vectors, if you notice that. Now, when you look at this vector u, notice x1 is common. It's like it's a scalar multiplied to every element in the vector. So I can write this as x1 times, so this is how the first one is written. So this u has an x1 common, and you can take the x1 out, and then you have this vector inside 1, minus 2, and minus 5. Similarly, the second vector, 2x2, x2 is common, so you can take the scalar x2 out and write 2, 5, and 6. So notice this. We started with the matrix product, and the matrix product is basically giving us a linear combination of the vectors. And what are these vectors? Notice this vector. The first vector, this, if you notice, the linear combination of vector 1, minus 2, and minus 5, which is nothing but the first column of the matrix A, and the second, vector 2, 5, and 6 is basically nothing but the second column of A. So your matrix product can be written as a linear combination of the columns of A. Do you see that here? That's a very, very powerful thing we're noticing. So a matrix product is written as a linear combination. Suppose if I say, hey, this is column A. So this one is, say, column A1. Or let's write it over here. A1. This is column A1. This is column A2. So this matrix product A times X is nothing but can be written as linear combination of the columns of A, which are given by A1 and A2. So it's X1 plus X2 times A2. So we can generalize the above concept. It was simply just a 3 by 2 matrix multiplied to a vector X, which is of size 2 by 1. So let's generalize it. If we have A to be an m by n matrix with columns A1 to An, and if X is an Rn, then the product of A and X, denoted by Ax, is nothing but the linear combination of the columns of A using the corresponding entries in X as weights. So, clearly notice this matrix product is nothing but the linear combination of the columns of A with the weights or the scalars are nothing but the corresponding entries in the vector X. Let's look at an example. How do we do it? So you have 3 vectors in Rn. We don't care where the vectors are, but they are all from the same n-dimensional space. we have a linear combination 3v1 minus 5v2 plus 7v3. So this is a linear combination of the vectors in Rn. We would like to write this as a matrix times a vector. That means this linear combination should be now written as A times X. Remember, your v1, v2, v3, these are vectors. So that means these vectors will become the columns of the matrix A. And the weights of this linear combination will become the entries in the vector X. So it's 3 minus 5 and 7. Okay? Now, let's see a relationship between a vector equation and, as the topic suggests for this session, is matrix equation. So that's what we will be doing next. Starting with the vector equation, we have vectors, say a1 and a2 and vector b, and we're looking at a vector equation x1 a1 plus x2 a2 equals b. So we already know how to write it down when we plug in these values of a1, a2, ab in this vector equation too. What do we get? We get x1 plus 2x2 equals 7 minus 2x1 plus 5x2 equals 4. Minus 5x1 plus 6x2 equals minus 3. So basically this is like equality of vectors here. But if you look at this sense, this one, notice I can write it as, this one can be written as a matrix multiplied to a vector. Okay, so this one, if you notice from here, notice this one. So now we have this in hand and we can go backwards. That's where it is coming from. So using the idea from equation 1, we can write this as a matrix A times the vector X. Now remember, we started from here. We're starting from a vector equation. A vector equation gives us this. And we also know a matrix product gives us this. So what we have done is that a matrix equation is not written like this. So what we started with a vector equation, we have changed it into a matrix equation. So this equation 4 shows a matrix multiplied to a vector is equal to the vector B. So this equation 5 has the form of AX equals B. Such an equation is called a matrix equation. Notice how we keep on moving between. We had a vector equation, we could see it as a linear system, and now the same vector equation can be seen as a matrix equation. Okay, some observations. Any matrix equation can be written as a vector equation. Also, we have seen earlier that this vector equation can be written as a linear system of equations. So, we see all the three are related. These three I'm talking about is a matrix equation, vector equation, and a linear system of equations. So if I'm given a linear system, I can easily write down a vector equation. If I'm given a vector equation, I can write down a matrix equation. So I can basically go between the three. So in other words, these are like the edges of a triangle. So I can easily go between here. Think of this one. So if I have a matrix equation, I can easily write it down as a vector equation. I can easily go between here. And if I have a vector equation, I can write down a linear system. So I can go between linear system vector equations. I can go between linear systems and matrix equations. So in other words, I can easily go between these three topics. So that takes us to a very important theorem. If I have a matrix M by N A with columns A1 to AN and B is in Rn, B is in Rm by the way, guys, this has to be Rm. Then the matrix equation AX equal to B will have the same solution set as the vector equation x1a1 plus x2a2 plus dot 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 xn equals b, which in turn will have the same solution set as the system of linear equations whose augment matrix is given below. So this equation, in other words, if we say a matrix equation has a solution if and only if B can be written as a linear combination of the columns of A, if and only if the linear system corresponding with the augment matrix is consistent. There it is. Now, the second most powerful theorem we will be using in this course is theorem number 4. It says, if A is an M cross N matrix, then the following statements are logically equivalent. Now remember, this A is a coefficient matrix. There is no way you see the word augment. Okay, so keep this in mind. It is a coefficient matrix, you guys. So if A is any M cross N matrix, thus, for any particular A, either all these 4 statements are true or all of them are false. Okay, for example, every B in Rm, this equation has a solution. So if every element in B in Rm makes this equation consistent, that's the meaning of that. It has a solution, that means it is consistent, which in turn says that every B in Rm can be written as a linear combination of the columns of A. Remember, because the matrix equation can be easily written as a vector equation, which from the vector equations section, the columns of A are spanning Rm, which ultimately says that A has a pivot position in every row. We will be only looking at this theorem. We're not going to prove this theorem at all. Keep this in mind. And also, a very important concept. Whenever any matrix is given to you, by default, it is a coefficient matrix, guys. Until and unless you see the word augment matrix given in the problem, do not assume it to be an augment matrix. That's what I'm trying to say here. Okay, so this was kind of a little theory, and now we're going to do some examples here. The first one, write a matrix equation which is equivalent to the given vector equation. Now, notice a vector equation, if you keep in mind, is nothing but written as a linear combination of the columns of A. So basically, this will be the first column, this would be the second column, this would be the vector x1, vector x with the rows x1 and x2. So the matrix equation, remember this is A1, A2, and your matrix equation we all know is AX equals B. So this one automatically is your B, but the matrix A will be made of columns of A1 and A2. So simply write down 6 minus 1 and 5, -3, 4, 0. And the variables will make the vector x, x1 and x2. You have to be careful. The first one, variable, when you multiply the matrix product, you should be getting this. Equals the vector 1 minus 7 minus 5. The x1 goes with the column A1. That's what it is. That's very important. So if you're writing A1 here, then x1 goes down. Be very consistent of how you're writing down. So notice what I do is when I write down the subscripts in my mind, I'm matching up the subscripts if I make so that I don't make a mistake. Okay, let's look at if a linear system is given, how do we write a matrix equation of it? Keep in mind, matrix equation is AX equals B. Now, B, this is automatically B, okay? And X is going to be composed of the variables x1, x2, x3. As you can see, each one of them has only x1, x2, x3. So when you're writing it down, make your life. Okay, I know this is x1, x2, x3. And B is easy because I am just going to stick with the way things are written. And also, before I start writing it down, I make sure how my linear system is written. The very first linear system is the way I take my clue from. The first one is x1, x2, x3, and all the constants are on the right-hand side of the equal sign. Make sure first that is written in all the equations given in the linear system. And once you fix the x1, x2s, x3s, and every other equation, make sure it is also written in that format. In other words, x1 followed by an x2 by an x3. So that way, when you're writing down the final product of the matrix equation, vector equation, you will not be having many mistakes. So when I'm going to write down the matrix A, basically, I'm going to remove the variable x1 and replace it by that. This represents my first column. In my mind, that's how I'm looking. x1 is related to the first vector. The vector is 4, 1, 8. That's how it goes. When I look at this one, oh, that's my first vector. Then the second vector is representing your x2. It will be 1, minus 7, 6. Third vector is going to be with x3. It's going to be 3, negative 2, negative 5. Guys, this is how I try to keep things in balance. And I know I will not have any mistakes. I'm just showing you how to play around with it. Okay, so this is AX equals B. Okay, now suppose if you're given a matrix equation and say, how do we write a vector equation? How do we write a linear system? That's what is the practice for the next slide. Okay, here we go. Here we have a matrix equation. This is my matrix A with an X and a B. Okay, B is very fine for matrix, for vector equations and linear system. B is going to be happy everywhere. It's the A and X which we have to play with. Okay, so now remember this is the vector A1. That's the first column is A1, A2, A3, and A4. That's how I write it down. So in my mind, I know what goes with what. Okay. Now, once you have fixed it, and notice why I'm doing it in such a way is because I'm making sure the subscripts are matching. Because when I write down a vector equation, if you recall, vector equation is what? x1, a1, plus x2, a2, plus x3, a3, plus x4, a4 equals b. And the reason is, I'm also making sure when I'm looking at how the vector x is, x1, x2, x3, x4, oh, great. Make sure this one is a1 because that's how the matrix multiplication goes. The first with the first, second with the second. So the first element of x will go with the first column of A. Second element of x will go with the second column of A. Third element of x will go with the third column of A. And fourth element of x will go with the fourth column. You know, those are the things. Suppose if instead of x1, x2, x3, x4, it was w, x, y, z. So you have to be very careful, okay? So let's write down the vector equation here. It will be x1, 5 minus 2, plus x2, 1, negative 7, plus x3, minus 8 and 3, plus x4, 4 and minus 5 equals the vector b, minus 8 and 16. Okay, let's write down the linear system of equations. The linear system is going to be simply 5x1, just do the matrix product. 5x1 plus x2 minus 8x3 plus 4x4 equals minus 8. Then minus 2x1, minus 7x2. Minus 7x2 plus 3x3 minus 5x4 equals 16. Okay? Okay. Now let's look at some examples from the book. These are from the section questions I've picked up. It says, given a vector u 2 minus 3 and 2, and a matrix A given by 5, 8, 7, 0, 1 minus 1, 1, 3, 0 is U in the subset of R3 spanned by the columns of A. Why or why not? Now notice it's in three different parts. U in the subset of R3 spanned by the columns of A. If you recall, some few minutes ago we talked about the spanning set of vectors. Okay? So what this simply means is U in the subset of R3? That means is U or can U be written as the linear combination of columns of A? That's what it means. This whole line means is U or is U in the span of A1, A2, A3. A1, A2, A3, the columns. If you go up, let me see which slide it was. That was in the beginning when we were doing a recap. Here it is. Slide number 4, guys. It says the span is called the subset of Rn spanned by these vectors. So it says, is U in the subset of Rn spanned by the vectors V1 to Vp? Now these vectors are nothing but the columns of the matrix A. Okay? It will take a lot of time, guys, but when you practice, trust me, it will help you. Okay, so if U is in the subset of R3 spanned by the columns of A, that means this matrix equation AX equal to U has a solution. Okay, what does that mean? If that has a solution, in other words, I'm going to write down the augment matrix. Okay, so let's write down the augment matrix. When we write down the augment matrix, what happens? We have the matrix here. These are the columns A1, A2, A3, and this is the vector B, which is of all the constants on the right-hand side of the equal sign. And then now notice I could have done many ways of solving it. I could have made this to be 0, but I wanted to just make my life easy. So I just, replaced R3 with R1. That's what I did. I just flipped it. I didn't want to multiply by 1/5. That's it, guys. That's the only story. So what I did was I did the flipping or interchanging of rows. I should not say the word flip. It's interchanging of rows, guys. Be more consistent with the terminology. Okay. Then I need to make this to be 0. Remember, we're looking for consistency. We're not looking for a solution. We're saying, hey, is it in the subset? In other words, is the matrix going to have a solution? So the only thing is, can we have a row echelon form? That's what you're looking at. Okay, so we make this 0 by going for the operation R3 minus 5, R1 goes to R3. We get this one, and then we need to make this to be 0. Remember, we have to write it in the row echelon form. So when we do it, oh no, what do we see here? When we do this operation, R3 plus 7, R2 goes to R3, we get a bunch of zeros and a non-zero element as the last column of the augment matrix. That's not right because theorem 2 is not valid. Let me get theorem 2 for you guys. It says, oops, kind of went to the back, guys. Okay, it says a linear system is consistent if and only if the rightmost column of the augment matrix is not a pivot column. That means there is no row of this form. But what do we see? We see a row like this. Not allowed. Okay, because of that, that means this matrix equation has no solution. As it has no solution, that means U cannot be written as a linear combination of the columns of A, or U is not in the subset of R3 that spans the matrix A. Notice how powerful is theorem 2, guys. This theorem 2 is in section 1-2 of chapter 1. That's where I am talking about from. Okay, one more example here. we have this matrix B, and we would like to know, does this matrix B's columns span R4? Say, oh, in other words, what do I need to do? Simply means Theorem 4. We just looked at it. Here, Theorem 4 says that if the columns of B are spanning R4, let me get the theorem for you. This is Theorem 4, guys. It says if A is an M cross N matrix, either the following statements are true or not. So if you have a matrix A, now that's, remember, it's a coefficient matrix here. And if it is a matrix equation you're looking from. So if this is a matrix A M by N, then notice if the columns of A span Rm, that means that matrix A has a pivot position in every row. Remember, either all the statements are true or all the statements are false. So if the columns of A will span, that means A has to have a pivot position in every row. And the negative would be if A does not have a pivot position in every row, that means the columns of A are not spanning Rm. Okay, that's what the question is. Does the column span? Okay, in other words, check if the matrix has a pivot position in every row. So keep that thing in mind, and we say, okay. Now my question is, do the columns of B span R4? So we need to see if there's a pivot in every row. That means, is my Theorem 4 valid? So what we do? Once again, we will apply the row reduction algorithm. We have this matrix B. You need to get, now this is very nice. The topmost, leftmost column has a non-zero entry. Great. And then everything I need to make is a bunch of zeros. Here 0. We apply R3 minus R1 goes to R3, and R4 plus 2 times R1 goes to R4. And this is the new matrix we get. And after that, we have to make a row echelon form. That means we start from top, then we go down, trickle down. Then the next non-zero row happens to be the second row, and this is the next pivot column. This is the next pivot column, and this is the next pivot. So pivot is 1. That means these two values should become 0. Okay, so when we do that, so in the next slide, I have to, so notice this next slide, I have taken it from here to here. And then to get these to 0, R3 plus R2 goes to R3, R4 plus 2 times R2 go to R4, and we get this new augment matrix. Notice, it's not in the proper echelon form, because in an echelon form, all the zeros have to be beneath the non-zero rows. So we will interchange these two rows. Okay, when we interchange these two rows, what do we get? Yes, we see an echelon form. But the question is, when we see this one, does it have a pivot in every row? Only pivot means a non-zero element. Only the first 3 have a non-zero element. The last does not have a non-zero element. Hence, Theorem 4 is not valid. Therefore, B, the columns of B do not span R4. Okay. Now let's look at some properties of the matrix vector product AX. That's Theorem 5. And here's the first time we start writing proofs. If A is an M by N matrix and U and V are vectors in, oh, I forgot, Rn, and C is a scalar, then a matrix multiplied to the sum of two vectors is the same as you do matrix product of A with U and A with V separately and then add these two. Or A times CU equals, if A is and U, that's another thing, it's CU, guys. A times CU equals C times AU. Okay, now we're going to start with the proof for the first one, that A, when added to a sum of two vectors, is the same as the matrix product separately and then adding them up. Now, To prove this one, guys, it's very important, first of all, by the equality of this equality means that the sizes are the same as well as the corresponding entries are the same. And when we are proving any results, we have to prove it generally. We don't prove it for using any numbers because that's not how proofs are done. So, going back over here, the proof for this one, what we're doing is we're to prove that the sizes are the same. So let's look at this one. A is an m by n matrix, clearly, and U and V are elements. This is an element of Rn. That means element or belongs to either of the same. Okay, so if there are two vectors in Rn, then U plus V also is in Rn, and the matrix product A times U plus V, what is the size? M by n times n vector of Rn means what? This will be a vector of size. I'm just writing it down to make it. This will be a vector of size m by 1, because remember U, so if we do A times U, so U is an n by 1 and m by n. So basically U plus V is in size having n by 1. So A times U is of size, so size of AU is what? An m by 1. The size of AV is also m by 1. So clearly A times U plus V equals AU plus AV in terms of size. So we have proved that the sizes of the left-hand side is the same as the size on the right-hand side of this equal sign. Now remember, these are matrices. Okay, now we have to prove that the corresponding entries are the same in each side. Okay, now we're going to prove the corresponding entries. So this is the matrix A. We can write it down in a general form, A1 to AN. These are, remember, I'm using these A1 to AN. These are columns of A. Keep that in mind. And U and V, now remember, if U is a vector in Rn, that means U can be written as what? U1, U2, dot, 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 Un. And V can be written as a vector, V1, dot, 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 Vn. So when I add U plus V, I'll get U1 plus V1 up to Un plus Vn. And then after that is a matrix product. So U1 plus V1 times A1 plus U2 plus V2 times A2 plus U3, V3 times A3, dot, dot, dot. Then it's just simple computation now. Un plus Vn times An. And then we can gather all the AIs, all the U1s and A1s together because we're looking at A times U. And all the VIs and AIs together. Okay, so we get U1A1 plus U2A2 dot 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 UNAN. V1A1 plus V2A2. I didn't write V3A3 because I was kind of having a problem with the space. So I just simply wrote here. So VNAN, that's another thing of a typo, AN. And this clearly is a vector from A times U, and this is a vector from AV. Okay, so that takes care of the first proof. Now for the next one is A times, okay, that's the typo, C times U. It's basically that it says simply if you're multiplying a scalar with a vector and then you multiply it to a matrix, it's the same as you do the matrix product and then of a matrix with a vector and then do a scalar. Now, as usual, the size has to be also checked because these are equality matrices. The size has to be the same. Now notice a U is a vector of the size n by 1. C times U will also be a vector of size n by 1. And then I do when A times multiplied to CU will be a vector of the size m by 1 because A is what? M by n, CU is n by 1. So this whole is a vector of size m by 1. Similarly, we already know what is AU. It's a size m by 1. And when C multiplies to AU, again, it will still be M by 1. So the sizes are correct, and now we have to prove the corresponding entries. So C times vector small u. So it's A1, A2, AN. That's the columns multiplied to, now this CU I've basically multiplied to every element of the row in U, vector U. And then it's simple vector, calculations here. So this is A1, this is a matrix product, A1 multiplied to C of U1 plus A2 multiplied to C times U2, CUN multiplied to AN. And then just, this is just parentheses. I can just take the A1 inside. And that's how the next equation is CU1 A1, the whole in brackets, CUN AN. Now notice I can take the C again out. It's just simple algebra. I'm just playing around with that here. So C times U1 A1 plus C inside brackets UN AN. And notice the C can be taken out common here. And what do we have? A1 U1 plus, U2 A2, does not matter which one you write first, guys. Because A1, remember, and U1, these are real numbers. Okay. U1 is a real number. So let me just be more consistent here. Okay. So it doesn't matter, but let me tell you that because U1 is a scalar. Scalar can be written in the front or the back, doesn't matter. But A1 is a vector. Plus U2 A2 ... plus UN AN. And this is nothing but the matrix product AU. So here our proof is done. Now, I would like you guys to practice on these problems. On section 1-4, 1-4, 6-12, and 17, 19, 21, 23, 24. Thank you.